Well, welcome back, everybody. This is the last session for today. It's a pleasure to welcome Tomer Ullman, a professor of psychology at Harvard University. The topic of this talk, as I mentioned before, relates to the previous session on knowledge acquisition. It's being inspired by how young children seem to understand the world already from their early days, and Tomer is asking the question, what is the formal conceptual structure that underlies these common sense understanding, this early common sense understanding about objects and agents. And then he goes on to provide several possibilities for models that can represent this background intuitive physics about how children essentially are learning to navigate the world. He'll present some work that captures early expectations about object solidity, cohesion, permanence, as well as rough-derendering. So let me introduce Tomer briefly. Tomer has actually an impressive amount of work on various aspects of common sense. He's a cognitive scientist that's interested in common sense reasoning and building computational models for explaining high-level cognitive processes and the acquisition of new knowledge by children and adults. In particular, he's focused on how children and adults come to form intuitive theories of agents and objects, and providing both a functional and algorithmic account of how these theories are learned. He received a Bachelor of Science from the Hebrew University in 2008 and PhD in Brain and Cognitive Sciences from MIT in 2015. Since then, he's been a postdoctoral researcher at the Center for Brains, Minds, and Machines, and he's currently an assistant professor at the Department of Psychology at Harvard. Thank you, Tomer, again for accepting this invitation and for providing a very complimentary insights into the problem of common sense coming from from children. And at this point, I'll just let you drive.
Great. So thank you very much for that introduction and for the invitation. I really appreciate it. So let's see if does this work? Can people see the slide saying this slide left blank?
Yes.
Okay, great. And I can still see you, which is nice because sometimes you're talking to a void and who knows. So let's see, does that, yeah, cool. Okay, so thanks again, Phil, for that introduction. And I also just want to thank the organizers in general for having me here. It's been lovely and I really appreciate the invitation. I also recognize, as Philip was alluding to, that my role here is as somewhat something of an outsider, and I want to spend a few minutes in the talk justifying why I'm here. It might be obvious to some of you, but to some others, you might need a little bit of convincing why someone who's interested in babies and infants and children and things like that would obviously want to participate in a session about AI and common sense reasoning. Okay, with that, let me also thank some funding sources over here rather than at the end. So here's an overview for the talk. Here's what I had in mind. We'll see how much we get through it because I want to leave time for discussion at the end. As I said, I want to spend some time just justifying why I'm here and motivating the relationship between AI and development and mentioning this notion of core knowledge that may be familiar to some of you, but not all of you. I'll then talk about a specific case study of core knowledge that is core physics. It's not the only knowledge in core knowledge, but it is something I want to focus on. I'll first of all talk about the phenomena, and then I'll discuss several possible modeling alternatives, AI and machine learning models for capturing this kind of knowledge. I'll then want to give you one specific possibility that we've been working on for trying to capture this. And then I'll talk about core psychology and doing kind of the same move all over again and discussing several alternatives as well as our proposal. And underneath all of this, I should say right at the beginning, is the idea that some of us have been pursuing in this program that combines people from Harvard and MIT and Stanford and IBM, with the idea that maybe what defines a lot of common sense reasoning is what we can all do from very early on. So our very early understandings about how people behave and about objects behave, stuff that is so basic that you might not even think that it's that surprising that we can do it, but turns out to be really hard to build into machines. And some of that will make more sense as time goes on, and then we'll have a discussion. But jumping into AI and development, just motivating that for 5 minutes, as I said. In case you haven't thought about it, I think that AI and cognitive development, babies and machines, have a lot to say to one another as fields. Even if you didn't know empirically that in the past these two fields have been in close contact with one another, normatively speaking, they should have a lot to say to one another. And that's not surprising because they're asking the same questions. They're dealing with similar questions of representation and learning, right? Representation, engineers, people in AI, people in computer science ask, what should I build in to my machine to achieve adult-like, human-level-like common sense reasoning and intelligence? Developmentalists are asking empirically, not normatively, what do we start out with in terms of our representations? What is built in versus what is learned? And for learning, we again have these questions normatively from an AI perspective, engineering perspective, computer science perspective. What should we build into our machines? What learning algorithms, what optimization functions, what loss functions should we build in to get human-like generalization and learning? And for people in development, we're asking empirically, how do children learn? And these questions are, of course, at somewhat odds with one another. You have a bit of a short blanket problem across these fields. If you can build in really complicated representations, but then it's not clear how you would learn any of them. You could build in really powerful learning rules, but it's not clear what representations you would end up with. Okay. Normatively, these fields are connected, but even not normatively, these fields go hand in hand. They go far back. How far back do they go? They go far back to even before the terms cognitive science and AI or even terms. They can be traced back at least as far back, the connection between them, I mean, to the seminal paper by Alan Turing, which I'm sure you all know, and to this paper that I'm sure you all know of computing, machine, and intelligence that famously introduces the notion of a Turing test, right? You know, we propose to take up the question of whether or not machines can think. Let's replace that with a different question, whether or not they can pass the later known Turing test. What's somewhat less focused on sometimes is that Turing then proposes how we should go about having a machine that passes that test. And he suggests that we should build a child machine because it would be way too hard to build adult level intelligence into a machine. Who knows what's going on there? All the facts that this thing would know, that's ridiculous, wink, wink. So maybe we should build in something more like a child, right? And then he goes on to say, what would a child machine be like? Presumably the child brain is something like a notebook as one buys it from the stationers, rather little mechanism and lots of blank sheets. So Turing's answer to the question of representation and learning is we start out with nothing, and we learn our way. I didn't mention this in the quote, but he talks about negative reinforcement, positive reinforcement. The machine does good and bad things. And we fill in this notebook through a process of reinforcement learning. And I'm sure many of you will hear echoes here of the dominant psychological view at the time, at least in the United States, of B.F. Skinner, pictured here. Now, Turing, in addition to being a genius, was a humble person, and he said opinions may vary as of the complexity which is suitable in the child machine. So it was more like, this is how I think it works, this is how I hope it works, because if it's not this, man, it's going to be rough to figure out how things actually work here. Now, of course, this is a very old view, and the idea now that we could start with absolutely nothing and learn our way into adult intelligence seems just completely bonkers unless you are the leading AI companies in the world. And many people are still pursuing this dream by Turing, and more power to them. But I would like to tell you about another view that's coming out of cognitive development. And cognitive development, I should say, is just like AI and machine learning and computer science, is a large and rich field. And everything I'm saying here is up for grabs and debated. And I'm not trying to tell you that like definitely cognitive scientists or child developmentalists think this. But this is a view, and this is a very powerful view, I think, with a lot of backing. And I'd like to tell you about it in case you don't already know this term, core knowledge, which is in the past few decades, we've discovered that Turing's notebook doesn't appear to be blank, or at least very early on, we can already say that it's not blank. And there's this notion of core knowledge. I dropped in a reference at the bottom for those who want to read more about it, is the idea that children have knowledge about the world. They have very early developing knowledge that is either early developing or innate, that this is shared with other animals, and that they know some things about some things from very early on, but it's about a limited number of domains. So not everything about everything, not nothing about nothing, but some things about some things. And those few domains include agents, objects, math, space, and depending on when you talk to Lispelke, possibly social relationships as well. These are general principles about a limited number of domains. So that might not be enough to get a sense of what core knowledge is exactly. I'd like to give you an example from the domain of physics, which will launch us into a discussion of how we can model any of this stuff, okay? But again, deeply related to common sense reasoning, in that a lot of us think that common sense reasoning is based on early understanding of how objects and agents behave in the world. All right, so infants have, from as early on as we can test, expectations about objects. This may be a shock to some of you, it might not be to other of you, but the way that we test this is we shock infants, not literally. We show them videos and we check to see how surprised they are. And the idea is that if they are surprised by these videos, that means that they had expectations that were thwarted in some way or violated in some way. So this is the violation of expectation paradigm. Just to give you kind of a sense of what that's like, suppose that you had this following display. This is similar in spirit to the kind of displays that people show infants. Here's a cylinder and two occluders. Watch carefully the following show. So the cylinder does that, and then you see this. And now I have a very simple question for you, okay? Feel free to put it in the chat or answer it for yourself. How many cylinders are there in this display? Okay, so if you're a child, you'll see this multiple times. Let me show that to you again. It's not a trick question, okay? Honestly, like how many cylinders are there in this display? Are there one? Are there two? A lot of you might say, well, there are two cylinders in this display, right? One stopped behind one occluder and it kept going, and another one appeared behind the other one, right? It couldn't have magically teleported. Now, of course, this is all PowerPoint and I can do anything I want. And the idea is that if I show you this, you might be momentarily tiny bit surprised. And if we show an equivalent of this happening in reality to infants, they would be surprised, suggesting that they expected that object not to disappear, and they thought that there would be two objects there. We can do similar things with videos like this. Watch carefully, the screen is going up, 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 up. And that moment is the moment where God is dead, right? Like it's not when the object disappears from view that you're surprised. Objects disappear from view all the time. What is surprising is that object getting crushed, right? Poor Teddy. Like that Teddy either disappeared or is maybe more malleable than I expected, or who knows what exactly, but you were surprised maybe by that. And certainly infants are surprised about it. So from these many, 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 many experiments over many decades, people have pulled this together into an idea that children have an understanding of the behavior of physical objects. And this is organized into a small number of principles, right, that these videos violate. The principle of permanence. Objects shouldn't appear and disappear out of thin air. The principle of cohesion, the principle of solidity. Objects don't go through one another like gossamer threads, smooth paths, contact causality, and several others, not an infinite number of others, but several others. Notice that these are a small number of principles and they are general. You don't need to learn them again for pucks and trucks and ducks and things like that, okay? They're meant to apply to objects qua objects. Once you've realized that something is an object, it shouldn't go through another object. Now, okay, maybe you believe me about that, and I suggest that you do, but that's an idea coming out of infant development. Still, even if you think that that's right, it's not clear how any of these representations are actually working, right? Like these are hard-won realizations, but they're not yet a computational model, right? We need some way of translating the sentence, oh, children are surprised when objects violate permanence or violate solidity or violate cohesion or contact causality, into something like a computational model, right? You can't just fire up TensorFlow or PyTorch or Gen or whatever it is you'd like to use and be like, if object violates solidity, raise the surprise flag, right? What even is that? So you and I understand that because we understand English, but infants don't understand English. So there's something else going on here. So there's been a surgence of interest in this notion that we could use something like the early understandings of infants to test the early common sense knowledge of these various machines. And like any good idea, once its time has come, it's been proposed by multiple people at the same time. This happens with bad ideas as well, but this happens to be a good idea. So what I'm showing you here is several benchmarks that people have proposed over the last 3 years. I'm not going to go into the difference between them, but they all share this idea of, hey, let's use these experiments that people have used with children very early on, most of them involving things like violation of expectation, and test them out on our machine learning algorithms and see if they are also quote unquote surprised, where that's been defined somewhat differently, but usually like a negative log likelihood of the next image or something like that, right? And of course, along with these benchmarks, you also have some models to test on these things. There have been several models proposed. There have been models proposed for years, I should say, for intuitive physics, right? Not just in recent years in both development and machine learning. I'm just highlighting some of the recent resurgence of interest in this and some of the recent models. There are new ones coming out all the time, both by people in these groups and from other groups. This is not meant to be an exhaustive survey. The key takeaway from this is people have been working on this. And also the people have been working on this in several different ways, but one of the key ways people have been trying to do this is with generic algorithms. And generic is not meant here as a value judgment, but in the sense of, I don't want to build in anything that looks like knowledge. I want to start with nothing, and I want to learn my way using a network that is not necessarily predefined for physics or objects or agents or space. One of these ones, for example, the feed-forward deep networks one from Facebook and Adam Lehrer et al. 2016 in the top left over there is very much an implementation of that idea. Let's use the same convolutional neural networks that we can use to recognize cats and dogs to do something like intuitive physics of stability and instability, okay? That's not the only one. There's all kinds of ones that run the gamut from like, no, we can't just expect to feed forward our way into this sort of thing. We need things like attention and memory, variational autoencoders and neural Turing machines and features and things like that. But a lot of these share the idea that we're going to somehow look at the visual image, pick out visual features of this thing, and then the same way that we reason about any video, we're going to eventually bootstrap our way into something like common sense reasoning. Not the only one. There's this interesting recent thing that just dropped 2 weeks ago. Okay. So these have been some proposals, but I want to tell you about a slightly different proposal, which we've been working with, which is from the camp of mental game engines. So again, for those of you, I'm doing some front loading here. For those of you who are not familiar with the notion of mental game engines, this is a proposal for adult intuitive physics, okay? The idea that adults have pretty good understanding of how dynamic objects work, right? They understand how things plop and flop and drape and crash and ooze. Everyday objects and everyday scenes, they have a pretty good grasp of this stuff. This is contentious among some people. But I think at this point we've amassed enough evidence that in everyday scenes and everyday dynamics, they're pretty good at this. And there's been the question of, okay, what's the underlying algorithm for this, right? What kind of, if we think that the brain is running something like a program, right? The mind is running something like a program, what's the program? And the suggestion from a bunch of people has been that maybe what they're doing is using something like the computations that are being used in game engines, in video games and things like that. It's a loose analogy, but it's a useful one, right? The idea that the same program that created all those different scenes, these scenes look visually very, very different, but they were all created by the same underlying software. This is a kind of software that has in it objects, and these objects have properties like mass, and there's things like dynamics and forces. And if you assume that that's how the world works, so there are objects and properties and dynamics, then you can predict, right? You can simulate how things will unfold over time, and you can then observe, make predictions about observations. You can also go backwards and infer, right? You can say, well, actually, I'm not sure what the properties are. I'm placing some uncertainty over this, right? In standard hierarchical Bayesian model generative format. You can condition on the data and go back and figure out what the posterior probability is on these various things. You can also generalize. Once I figured out that this thing is heavier or lighter than I thought it would be, I can generalize to entirely new scenes that don't have to do with, visually speaking, with the one that I just saw. Now, this idea has been around for a while. Some of the people who have pioneered it are Peter Battaglia and Jessica Hamrick, now at DeepMind, but there's been a lot of other people. If you'd like to get my view and several others, here are some papers over here that you can look at for how specifically these game engines relate to common sense reasoning and how they relate to early on understandings in infants. Okay. So taking that as our starting point, which is a bit funny because it's the end point for adults, right? The idea that the way that I can reason at least about the fact that, hey, you know, if I drop this, what's going to happen? It's not going to break the table. If I throw it at the window, it's not going to go through the window. I have a sense for how this thing is going to work in reality. Maybe what I'm doing is running something like a game engine simulation-ish, right? Even if you think that that's the adult state, and you do not have to accept that that is the adult state, as I said, the stuff is contentious. I'm going to leave open the Q&A for later, but these are, I'm already seeing some good questions there. All right, even if you accept that this is the final adult state, what do we think infants have, if anything of this? Do they have nothing and they somehow learn something like a mental game engine? Do they have the mental game engine from birth? We put forward a proposal recently that maybe they have something like a minimal game engine, right? And I'd like to give you one proposal for how that proposal might work, but this is a work in progress, as I said, as part of this machine common sense reasoning program that's shared between IBM, Harvard, MIT, and is happening under DARPA. So again, a full mental game engine as adult, but the minimal game engine starts with approximate objects, some notion of dynamics plus collision detection, priors and resample, which I'll explain in just a second, over these properties, like where you expect objects to be and how many of them you expect to be, and some minimal notion of tracking. Now, I don't have enough time to go into all the details. I'm going to give you like a high-level summary of it. But those of you who want to read more about it, there's this NeurIPS paper from 2019. I'd like to particularly highlight the role of Kevin Smith in all this. Of course, everyone here contributed a lot, but in particular, Kevin was instrumental in all this. So this notion, this particular model that we put forward we called it Adept, for approximately render extended physics and tracking. I'd like to give you a brief notion of how that's supposed to work. So the idea is that you have these scenes coming in, unfolding over time. You have an image, pixel-based image, and we do avail ourselves of some neural networks for doing de-rendering. This is the work of Jiajun Wu, who spent a lot of time on this. The idea that you can take an image, and the output of this should be to some sort of structured understanding, to something like a game state at the end of it, okay? So you can imagine like a game state already, quote unquote, knows about objects, and objects here are very simplified geometric things. There's a limited library in this model of things like spheres and cubes and things like that. And it basically sees these bunnies moving around, let's say, and it tries to figure out the approximate de-render is just how many objects are there, where are they, and basically so basically the nearest fit cuboids or spheroids to this thing, their size and their velocity and things like that. But that gives us a game state, right? It tells us like, okay, these spheres are over here taking up about this much space, moving at about this velocity. Now we know how dynamics work in this world. We know how physics works in this world, and we can basically move it forward in time, however many steps we want. And we can give that's our expected observations. Now time stops for no person, and more images come in, more images get de-rendered. Those de-rendered game states are compared to the predicted game state. So the comparison is happening not at the pixel level, but at the level of expectation of, should there be an object there? How big is that object? Did the object appear or disappear? Right. So, and we include a notion of something like, basically, to put it in a somewhat blunt fashion, it's not exactly accurate, but to say, can magic happen, right? Every so often, something really weird might happen. It's this very, very, very low probability. In a slightly more technical term, we say that we include in the standard dynamics, the dynamic unfolds either according to physics, or we always include room for resampling from the prior. The equivalent of closing your eyes and then opening them again, and you have some expectation of what you're going to see. Okay, so you do this, and we basically wanted to create several scenes that mimic the experiments that we know infants can pass at around 4 months. Okay, so experiments that target the kind of things that you saw before with the cylinder and the teddy bear, these principles of creating, vanishing, blocking, and things like that. And I want to just show you what these things look like. First of all, there is training here, okay, but the training doesn't involve any learning over physics at all, basically. The training is sort of the equivalent of learning how to see. Okay, so you have objects moving around, and what we're training is the de-renderer. We're training the part of the model that is kind of saying, okay, from these pixels, which objects fit this scene the best? That is the location and number of objects and how fast they're moving. That's all we're doing for training. In testing, you're seeing scenes that don't look like that, right? You're seeing something rolling around like this and violating solidity, right? I'm guessing all of you saw the violation of solidity there, or here's an example of like something vanishing, if I remember correctly. So 2 objects enter, 1 object leaves. It's the Thunderdome for infants. Here's another one. So I'm just checking time while you're looking at this. So that one looks like there's probably 1 object there moving around, but then, well, you can tell by my voice that actually there's 2, which is surprising. This one I'll skip over, but okay. I want to give you kind of a view of what kind of, quote unquote, the model sees in all this. So we then test the model on these test scenes, and we want to see whether or not, how surprised it is. So here's an example scene, right? 2 objects go behind the occluder. One object comes out, the occluder comes down, that object is no longer there. So their model includes a notion of basically particle filters, particle tracking. Each one of these particles is tracking something like a belief state. And from that, we can read out how many objects and where the model expects there to be, okay? So here you're seeing these particles, right? Like, okay, the objects are basically there. Oh, it stopped behind the occluder, it's still there. Even though it didn't come out, the expectation is that it's still behind the occluder until it is no longer there. And then there's nothing to it but to make those particles disappear, which is a surprising operation. If you want to see it in terms of like surprise as kind of negative log likelihood, there's a small spike, relatively speaking, when the object doesn't come out when it should. There's a much bigger spike when that occluder comes down and the object is no longer there. Similarly for objects appearing and disappearing, right? So there, this is an interesting case because you probably did a double take, right? Something like, oh, well, that yellow ball, I guess didn't expect to be there, but in retrospect, it was probably just there all along, right? So the idea is you start out thinking like, okay, here's the green ball, I'm tracking it, tracking it, tracking it, tracking it. Oh, I need to create another ball. And that creation of another ball is momentarily surprising, even if in retrospect, you can fix it and say like, oh yeah, that makes sense. I know how to recapture this scene. Okay, here's basically the equivalent of the teddy bear, right? The thing goes over, and that's surprising, and then it comes back. And for some of you, that might be a double surprise because you thought it disappeared. So similarly, again, the model Adept isn't surprised that the object disappeared from view. The moment of surprise is when it's no longer physically tenable for this thing to have happened. And as far as Adept is concerned, the object shouldn't be there, so there's a moment of double surprise. Okay. We can basically create all these scenes and we can run a whole bunch of quote unquote experiments on this stuff, testing various levels of generalization, right? Like we can train this stuff on certain objects and test it on objects that look nothing like the objects that it was trained on. And we can compare this to a bunch of standard models that have been proposed in the literature, like these encoder decoders and GANs and LSTM. And the idea is that Adept does better than all of them, and we take care to make sure that it's not just right. One of our pet peeves is that there's no confidence intervals on some of these papers, so we want to include, even within confidence intervals, the model does better than all these, especially when it involves generalization. So some of these models seem closely tied to the fact that, you know, it has to be the objects that you were trained on, similar to scenes that you've already seen. For us, it doesn't have to be that case. Now, we compare this also to human studies where we showed humans these same things, and we asked them, how surprised are you by these scenes? Adept is closest to people by a factor of 2, but by no means perfect in the sense that it doesn't perfectly predict what people are doing in this sense. So V and X in that sense. We also want to test the finer grain level of surprise here. So not just how much people are surprised by these different scenes, it's not a binary distinction, right? Like, oh, these are the surprising things, these are not the surprising things. Some things are more surprising than others, right? Some things are more impossible than others. And we ask people to give us ratings of those things. We also ask them, when is it surprising, right? Like just press the space bar when you think it's surprising. We can compare that to our models. Why is it surprising is another question that we can answer. This was in CogSci 2020, and we're preparing it also for journal submission. And again, I'd like to highlight the role of Kevin Smith in all of this. I don't have time to go into the results there, except to tell you that basically Adept we're able to read out all this data from Adept. We gave an honest go to a series of other models, and they basically can't predict a lot of this stuff, right? Like when should something be surprising? I'm not saying they cannot, that these other models that are coming out that don't build in this stuff can't do it. I'm saying it's a challenge for them, and I'd be interested to see what they come up with. Okay. So Adept is one model. It's one proposal for how infants might have these, so this kind of ability to pass these early common sense reasoning tests in physics. And we think something like that is still underlying your intuitive physics as an adult. It is important for me to stress that this is one proposal. It's under active development. It's just one thing that people have been considering. And I'd also like to stress the role of physics hacks here, right? This was absolutely not a perfect simulation. It was very important that it wasn't a perfect simulation. And we have a paper from a while ago that we've been chasing down now with a series of follow-ups on all kinds of approximations, workaround, principled stuff that engineers and computer scientists have come up with to make their simulations work in real time, and how that may play into the kind of findings that we're seeing in infants. One particularly important one that I just want to highlight is this notion of body and shape that some of you may be familiar with, right? Shape is the kind of thing that gets rendered onto your screen. It really matters for us to be able to recognize that this is a duck. For that, it really matters that it is yellow and has this particular texture and this particular lighting, that its beak looks like that. For the purposes of object tracking, are these objects going to hit one another? Where am I going to catch this object? The underlying representation that a lot of game engines have is actually this kind of dualism. There's the physical body that is an approximation of the thing that gets rendered out into the screen. Sometimes these approximations are very rough. And we use very rough approximations in our own models, which is one of the ways we're able to get this kind of generalization. Now, Yichen Li, who's a student working with me and Josh Green, has been chasing down this idea in adults as well. So we think adults might be using something like this approximate reasoning in their physical simulations and things like that, and has been finding some very interesting stuff over there. Okay, in the 5 minutes I have left, I'm going to cover core psychology, but don't worry, because a lot of it is basically going to be, so hey, remember core physics? That, but for core psychology. So it's not going to take us the same amount of time as it did for physics, okay? So I'm going to run this a bit more quickly because you already have all this front-loaded knowledge. Just like we have expectations for how objects will behave, we have expectations for how agents will behave, and they're not the same expectations. We all have this as adults, okay? And we have this cross-culturally, and we have this across time, right? One of my favorite quotes from Marcus Aurelius is him saying, what is such a person doing, and why, and what is he saying, and what is he thinking of, and what is he contriving, right? And it's not just for Roman emperors 2,000 years ago, it's for babies, right? Babies also seem to have thinking about other agents and having expectations that agents will have goals, that agents are efficient, that agents can defy physics. Again, these are hard-won realizations from decades of research, and yet they need to be translated into something like a computational model. And people have all given all sorts of computational models, right? These are kind of scenes, by the way, that you can show infants and the kind of stuff that we're working with, both with infants and with our computer models. But the idea is that a lot of this can be captured if you assume something kind of like a simulator, but instead of a simulator for objects, a simulator for agents, or in other words, a planning algorithm, right? The same thing that people have been using in economics and robotics and planning and decision-making, things like that, just invert that, okay? So if you assume that there's such a thing as agents that have utilities and rewards and costs and things like that, then you can forward predict how they will behave, right? This is an agent, that's an apple. The apple is not an agent. The agent wants the apple, right? So you can predict that the agent will move towards the apple. Seems almost trivial, but again, it's very hard to build machines that can reason in the same way that adults and children can about this stuff. You can also do inference. I don't know what this agent wants. If I see him moving towards the apple, I infer that it wants the apple, and I can generalize to what it'll move to in the future. Now, a lot of people have studied this notion of inverse theory of mind, inverse planning, action understanding as inverse planning. I'll highlight specifically Josh Tanbaum, Chris Baker, Rebecca Sachs, Julian Jar Ettinger, not the only people, but certainly movers and shakers in the field. And again, there are alternatives here that rely on features, and I'm happy to get into that maybe in the Q&A. But just to say, we again took this notion and said, okay, what's a minimal kind of planning engine, and can we build a kind of benchmark that would test this idea, taking the same kind of studies that people have used in infancy and testing various models against one another. Here we call this agent for action, goal, efficiency, constraint, and utility. And one day, I'm sure our field in general will stop it with these silly acronyms, but today is not that day. So this is very much the work of all these people who are mentioned here, and I encourage you to go over to that link and check out this work. I want to highlight in particular the role of Chun-Min Shu and Abhishek, but in particular the role of Chun-Min Shu, because he's also currently on the job market, and people should snatch him up. He's one of the people doing the most interesting work on combining social reasoning with physical reasoning in development and beyond. So we showed the machine examples of these scenes, which are the same sort of things that you can show adults, the same sort of things that you can show EEG experiments, right? The same sort of things that you can show babies. And what you're seeing here is an agent moving towards a goal. Now, what do you expect to happen if there's no occluder, right? Or that the barrier is on the other side? Most adults expect the agent to now go straight, right? But consider that the other alternative, the one that we quote unquote call surprising, is only surprising if you think of this as an agent that has some sort of cost function that it's trying to minimize in order to get to its goal. From a purely statistical learning perspective, there's nothing wrong with the agent repeating exactly the trajectory that it did before. It's only surprising in that that trajectory is inefficient, right? And again, even infants can reason about that sort of thing and are surprised if the agent takes the inefficient path towards its goal. So we created all these sort of scenes to test these early notions of agents to be efficient, agents should have goals, we can reason from their actions to the constraints. And we placed a particular emphasis on trying to generalize from one principle of core psychology to another principle of core psychology. Okay, we really wanted to get away from the notion of, oh, just randomly sample IID from 1,000 videos, use whatever network you want to train on, 80% of those, and then test on the other 20%. When you do that, yes, the networks can pick up on like very low-level statistics that are not that interesting. But if you train on only subparts of it and you try to really run the hard generalization that we have in this benchmark, lots of current things have basically been, they don't generalize that well, right? This model that we've been proposing, the reason that it generalizes so well is because it has a notion of planning and physics and things like that. Okay, and with that, I think, yeah, I left 9 minutes. So I think we wanted 10 minutes for the discussion, so there we are. Let me mention as like key points for the discussion. So I'm gonna take 30 more seconds of your time to like recount the hero's journey that we've done here, okay? The first one was AI and development are connected. If you haven't thought about it before, I hope that you realize that they are empirically and normatively, okay? The proposal coming out of some corners of development is that Turing's notebook is not empty. Babies have a lot of knowledge and understanding about the behavior of other objects, other agents, and we think that this forms the basis for later common sense reasoning about people and things. I didn't get too much time to talk about this part of things, but we think in general, hierarchical Bayesian models, generative models, bridge core knowledge and intuitive theories. If you want to hear more, we have this annual review piece out now. This is a freely available version of that, and I encourage you to check it out. I'm really proud of that paper. And another thing I'm happy to discuss is the notion of abstraction and approximation, which these simulations are not perfect at all. And I think that there's a lot to be said for using approximation and using approximations in engineering as working hypotheses for what infants and adults might be using. Okay, and with that, thank you for your time.
Very interesting. Thanks a lot, Tomer, for the great talk. You covered so many interesting topics, I think, and it's core physics, core psychology. I know that there is a lot that goes into these, and I think you did a great job in kind of keeping that on a higher level. So let me start by the questions in the Q&A chat, and then we can go from there. So Bart had actually 2 questions. Bart Salman. You mentioned the concept of an object. What is known about how an infant gets to that key level of abstraction, whether that's learned or innate?
That's such a good question, and I wish I had a definitive answer for that. But that question basically summarizes like decades of arguing back and forth in the developmental literature, in the cognitive literature, in the comparative literature with non-human animals and things like that. You'll definitely, I mean, this goes back hundreds of years to the basic questions of empiricist versus rationalist debates and things like that. I think that there's room to say that, at least according to a lot of these core knowledge proposals, infants don't learn what an object is. They are basically pre-programmed to have something like that understanding. Now, it's not magic in the sense that somehow evolution has built in that notion into it, but a lot of us don't think that you learn that from scratch. It's not that you basically get pixels and from pixels you somehow get objects. To wit, a lot of the other models that I mentioned, one of the reasons that I think that they don't generalize as well, and I don't mean that as shade, I think that a lot of people who worked on those models will agree that they don't generalize as well. And when they see our results, they say, well, you're cheating. You built in a notion of objects. And we're like, we're not cheating. That's what you need. You need to build in a notion of objects, right? Still, I totally understand where they're coming from, but they want to somehow bootstrap, learn that notion of objects. And again, it's not magic. It had to have come from somewhere, but we suspect it might not come in through development. It might come in through evolution, which is a whole other beast. And again, I think it's telling that if you look at the last decade or so of research in some of these other models that try to do things in a bottom-up fashion, they're gravitating. This is a very parochial way of putting it, by the way. Like, you can argue with anything I'm saying here, but from my perspective, I think there's been a shift towards like, well, actually, we can't just convolutional neural network our way into it. Maybe if you'll allow us a notion of an object, then we can do it. And I don't want to put words in Hinton's mouth, but the last I heard him talk about some of this stuff like 2 years ago, he's also like, all right, it's the only thing that's my Hinton impression. It's terrible. I'm sorry. I'm not going to do an accent. All right. That's the only thing that I will grant the native is some notion of an object, and maybe capsules is the way to capture that. So even if you grant, by the way, a notion of an object as innate, other people have other answers to it, something like an object file, or something like a geometric body, or something like, various networks have tried to then incorporate that into their structure. But yeah, I think sorry, that was long-winded, but I think it's viable that kids don't learn that.
Okay. Yeah, thanks. So, I mean, there are two more questions that kind of go to these questions of, what is innate and what is, learned. So let's just take one more of them, and then we can go ahead with, maybe other questions. So one would be, so Yolanda asks, I'm curious about what types of objects may be known to infants at the start. For example, is heavy one of those types, or just physical objects as a general type?
That's a really good question. So I think translating that into some of the language that we're using, we might make the distinction between things like properties, right? Like which object properties are known early on. So exactly things like elasticity and weight and roughness and stuff like that. The honest answer is that we're not sure. So some of the experiments that we're running now have been trying to push that down in age, and we're seeing some interesting things that I take to suggest that infants at around a year old have an understanding of heavy and light, and certainly some of the work by René Balajon, for example, suggests that they have an understanding of heavy and light at around 6 to 8 months or things like that. And 6 months or 8 months matters a lot here, but I'm kind of glossing over that. That's not the same as saying that they understand heavy and light from the beginning. And it's just so hard with infants, because it might be that they are predisposed to understand that, but then connecting it to the actual array that they're seeing is very, very hard. And I'm certainly, by the way, I should mention, this was a very nativist talk, but like, I certainly think infants learn a lot over the first year of life, obviously, in many domains, but certainly also in intuitive physics and intuitive psychology. I do buy a lot of the evidence that suggests that they learn a lot about support, that they learn a lot about momentum, right? But there's different ways of understanding that. Some way of understanding that is they somehow they bootstrap the notion of weight from not having it. Another version is they understand weight, they're just very, very fuzzy about which objects say what, and even things like bigger things are heavier, or stuff like that is something that might be priors that you need to adjust in the sense of a hierarchical Bayesian model. By the time we're adults, I think there is an argument to be made that we intuitively parse physical objects in the sense of like their elasticity and weight and things like that. There's some really beautiful work coming out of Nancy Kenwisher's lab with her students, Sarah Schwetman and other people, suggesting that there are dedicated areas for the notion of things like weight. And again, like abstracting away from this is a duck, this is a truck, like this is heavy, right? I'm not sure that fully answers it, but
I think it does. I mean, I guess for a full answer we'll need hours, but I think this gives a very nice, insight into this. So a question that I had, Tomer, is so we're talking a lot about this sort of this sort of acquisition of knowledge over time. I was wondering, is there, so how much knowledge is there about the role of analogical transfer and kind of knowledge transfer across time? And how does that basically help people learn over time?
That's again, you guys are asking, you all are asking very good questions. And the short answer is, it's complicated. I think it depends what you mean by analogical reasoning, right? Which is kind of the weakling answer. And there's a lot of people who have studied analogical reasoning. And I think that there's a lot to be said about the role of analogy in learning and things like that. I'll say two things that I think relate to our early understanding of that I feel more comfortable talking about and espousing about like a core understanding of objects and agents and things like that. I think a lot of our analogies rely on a kind of abstract transfer, right? Like I'm now in a pouring situation. I'm in an uh-oh situation, right? What does an uh-oh situation mean? Right, like in this, I'm going back to some work by Alison Gopnik, right, showing that children don't understand just words like very early on, like ball and wall. They seem to understand very early on words like one of the first words they produce is stuff like uh-oh, right? That's a completely different beast than ball, even though ball is very hard, right? Like uh-oh implies there was an agent and the agent had a plan and the agent had a goal and the plan didn't work out, right? And now if you have that more abstract notion, you can make analogies in the sense of like, this is an uh-oh situation and that's an uh-oh situation, even though they're completely visually distinct, right? Or this is an all done situation and that's an all done situation, right? Even though one of them is about music and one of them is about your teacher telling you to finish your food and things like that. So I think that a lot of that early on analogy trades in the kind of concepts that form a part of physics and psychology: agents, objects, plans, intentions, goals, physical bodies that can undergo physical interactions. They don't come for free though. And I think that a lot of work in the next few years is going to be focusing on things like, how do we take stuff, even if you don't have to buy it again, but how do we take stuff like these structured generative models and abstract away stuff like pouring and failure and stuff like that, right? They're not, even if you buy the game engine analogy, and it allows you to pass 4-month-old physics, or to tell you that like the tower's fallen down or something like that. Nowhere in there is the word fall, right? Like if you, again, by a very loose analogy, consider that if you had like those who play Zelda Breath of the Wild or Link, whatever, my kid plays that, so that's why it's on my mind. You can use something like that engine to make predictions. What will happen next? I'm going to throw this rock, it's going to hit that troll, the troll's going to fall, things like that. The engine doesn't contain the notion of, well, some of these do notions of plans, but they don't contain notions of like what the word pouring is, right? Or supple or stuff like that, which we trivially do, but they sit on top of that representation, I think. There's more to be said there, but I'm happy to talk more with people offline if they want to.
Perfect. So we are 1 minute over time. Maybe we can take 1 or 2 more questions if that's okay.
Yeah, sure. Okay. Sounds good.
Okay, so there is one more question from Bart saying, is there a real technical need to incorporate innate knowledge in AI systems if you view evolution as just another form of learning from the environment?
That's a very good question. And it kind of depends on like how much compute time you have and how many resources and also what your end state is. It's a really bad idea to bet against all this deep learning stuff, because whenever you try to bet against them, they'll usually find a way of, bootstrapping from just a huge amount of data or things like that. I'll go out on a limb and say yes. I think that there is a need to incorporate this stuff. And I think also that it's not the case that, just learning works differently, as Bart, you yourself are saying, right? Like it's maybe just a different form of learning. It's a very different form of learning to say it happens through evolution or it happens through gradient descent. And again, I don't mean to straw person this here, but it used to be the argument that like, we can train our networks to recognize cats from dogs or something like that. And it takes them a bazillion, now less, but it takes them like a lot of samples and they kind of improve slowly over time. And that's not what children's recognition seems to look like. They need very few samples and they generalize wildly, right? And they're like, yeah. Well, actually, the adults can do that, sorry. And they're like, okay, so that's what children are doing. Early on, children need to learn all this stuff. And as an adult, you can do fast generalization. It's like, no, children don't do that. It's like, oh, okay, then what that is capturing like evolutionary time. But consider what that would mean for evolutionary time, right? That would mean that you're committing to a Lamarckian view of evolution. That's like, I'm going out in the world, I recognize an instant of a cat, I change my network, I somehow pass it on to my kids, and then I die. My kids start out with that state in their network of having seen one example of a duck or something, or 10 examples of a duck. They then gradient descent a little bit more, they see 10 more samples, then they die, somehow having bequeathed that neural network onto their children. Like that's not how evolution works, right? And I think it's important that that's not how evolution works. I think there's all sorts of arguments just normatively, right? Even as an engineer, like that for the most basic stuff, if you think of these as, again, programs, you're searching over program space. And basically you're trying to find the program that generated the data. That's what we're all doing, right? As scientists, we're trying to find the theory that generated the data. As children, we're trying to find the intuitive theory that generated the data. See the work of people like Susan Carey and others. As infants, we're born with programs that generated the data, is the claim, right? And again, I'll point you to the annual review that tries to tie all this stuff together. If you just run like an optimal Levine search or whatever over all the programs that could have generated some given set of data, it'll take you so long for even very simple programs and data. Like, wouldn't it make sense for evolution to give us a leg up there? And don't we not want to recapture like a bazillion years spending that? I think a reasonable answer, by the way, is no. And a lot of smart colleagues have been making good arguments for like, no, we actually still want to build systems that will eventually discover core knowledge in whatever way. I think that's useful. I'm glad they're doing it. I think we want to spend, at least some people need to spend some time on this alternative proposal.
Okay, I mean, thanks a lot, Tomer. I have more questions, and I'm sure other people have tons of other questions. This has been very refreshing, and I think giving us a nice complementary perspective. So yeah, thanks again for taking the time and energy to prepare this talk and to give this talk for all of us today. I would also like to thank all of the speakers and chairs of today. So tomorrow we continue, same time, 9 to 12 Pacific. We have 2 more sessions. One, in fact, I'll briefly share my screen. So, we covered the sessions on common sense reasoning and common sense knowledge today, and the keynote by Tomer Ullman. Tomorrow we will talk about common sense for creativity, which includes things like biases, which was one of the questions of today. We have another session on common sense in AI agents and robots, so basically in embodied agents, and we'll end tomorrow with a panel on artificial general intelligence with Catherine Havasi, Ken Forbes, and Vered Schwartz. Thanks everyone for the participation, and we will see you all tomorrow.